Okay, so we're starting module 4B. In this module, we're going to talk about two streamlined circuit analysis techniques, just like we did in 4A, but in these two techniques, you're really only solving for one voltage or current at a time. So nodal and mesh, once you solve the node voltages or the mesh currents, you can solve for every other voltage and current in the circuit and solve for power. That's not going to be the case for superposition, which we're going to talk about now, and then equivalent circuits, which we'll talk about next. So that's one of the distinct differences between the two. So we're going to start with superposition. Okay. And superposition works on circuits that are linear, or we can use superposition. For circuits that are linear. Okay, and linear does not mean a straight line. We'll talk about this in just a second. But linear circuits have two characteristics. One, we have additivity. And then the second one is homogeneity. Okay, additivity is kind of easy. Homogeneity is a little bit more complicated. So let me show you what additivity is. So let's start with additivity. So let's say we have a very simple circuit. This is actually just going to be a plain old voltage divider. So we have Vs, a voltage source Vs, and we have two resistors, 4 ohms here and 6 ohms here. Okay, and we're going to solve for this voltage. We're going to solve for this voltage Vx. Okay, now if we were to do that using plain old voltage division, we know that Vx is equal to the total source voltage Vs multiplied by the resistor we want to know about divided by the series combination of the two resistors in the voltage divider. So Vx is just equal to Vs times 6 over 10. Okay, so what happens if Vs is equal to 20 volts? If Vs is equal to 20 volts, then Vx is going to be plugging 20 here into that equation, then Vs is going to be 12. Okay? Now, what happens if we didn't have a 20 volt source? Let's say for argument's sake. Let's say that instead we had two sources. We had Vs1 was equal to 12 volts, and we had Vs2, which is equal to 8 volts. And we put these in series with each other. Okay, so basically what we'd have from a circuit standpoint is two voltage sources in series, 12 volts and 8 volts. And if we were to write a KVL equation around this node and solve it, we would get that Vs, or around this loop, excuse me. So KVL equation around this loop. Okay, then what we would get is that Vs is equal to 20 volts. Okay, so if we look at Vx1 and Vx2, the values of Vx here as a function of two values of Vs, okay, we'll have that Vx1 is going to be 7.2 volts. Okay, so I'm just plugging 12 in for Vs into that expression, okay, and then Vx2 is going to be 4.8 volts. All right, again, just plugging 8 into that voltage divider equation. If we add these two voltages together, kind of like we did for this KVL equation, we'll get that total 20 volt source voltage. If we add the two Vx's together, Vx1 and Vx2, we will get 12 volts, which is exactly what we would expect Vx to be if we put a 20 volt source in place. So looking at this, if we we can think about 12 and 8 being a function of additivity. If we add voltages together at one end, we can look at another voltage and add those sub-voltages together to get the same total voltage, okay? And so all linear circuits will allow such a thing to happen, all right? So this is additivity. Now let's look at homogeneity. I think I spelled it wrong up here. No, I didn't. Good. So homogeneity. So homogeneity is a little bit more difficult to explain definition-wise, so I'm going to explain it this way. So let's say we have just a box for a circuit element here. And this is I, and this is V, and it really doesn't matter here whether whether the circuit element is active or passive here. Okay. So if we look at this, okay, we have if we were to look at a plot of the VI curve here, so we're going to put I here and V here. Let's say that this curve looked like this. Okay, so and we had a different element. Still our IV curve here. And let's say that that one looks like this. Okay, so here V is equal to K times I, okay, where K is the slope of the line, right? Okay, and if we increased K by some factor, or excuse me, if we increase the current I by some factor, so let's say we let I equal 2 times I, then we would expect the voltage V to equal 2 times the original voltage V, right? Okay, so so this is an example of homogeneity. Now if we look over at this side, V is equal to Ki plus B, right? We have some slope, and let me use a different one because I don't mean the same. K equals Mi plus B, let's say. Okay, so this looks more like the equation of a line that we would recognize, all right, where we have a slope and a y-intercept. Okay, so the line is still straight, but it's not homogeneous because if we multiply I by a factor, again, let's say 2, then V is equal to 2Mi plus B. V is not equal to 2 times the original voltage V, right? Because when we multiply the current by a factor, we don't multiply the y-intercept. Okay? So while something might look linear, it's not necessarily homogeneous, which means that it doesn't satisfy our linearity requirements. Okay? And all the circuit elements that we're going to talk about in this class, resistors, inductors, and capacitors, all satisfy that rule. Okay? So they're all homogeneous. All right, so let's talk about superposition and how we're going to use it. So, superposition steps. So step 1. We are going to identify all independent sources in the circuit. And this is important. All independent sources. Okay? I'm going to put a box around it. If they're not independent, it's going to change how we approach the circuit. Okay, so we want to identify all independent sources in the circuit. And we're going to call that number n. So we're going to have n total sources. They can be voltage sources or current sources, but they have to be independent. Okay? For superposition, n has to be greater than 1. We're not going to do superposition on a circuit that only has one independent source. All right? Step 2. And note that we're going to do an iterative process here before we start this. So we're going to turn off n minus 1 of the sources. Okay? And when we do that, we'll be left with the circuit with all the sources off but one. Okay? And so step 3 is we're going to solve for a certain current or voltage. Okay? So a certain current or voltage. Okay, so what we've been asked to solve for the circuit. All right, so we're going to solve for that current or voltage. Okay, and then we're going to come back up here to step 2, but we're going to turn off a different set of n minus 1 sources. Okay, so the goal here is to iterate until each source has been on one time. Okay, and once each source has been on one time, then you will take all of those parts of the voltage or current and you will sum them together. So once each source has been on one time, you will sum the parts of the voltage or current. And this may seem hard to understand right at first, but I think when we do our first example, this should all come together. Okay, so if we have n independent sources, then we're going to solve n parts of the voltage or current. Okay? So we have to turn off these sources. Let's talk about how we do that. So, how to turn off a source. Okay, so let's think about how we turn off, or what we want to occur when we turn a source off. So if we have a voltage source, we want that voltage source to have 0 volts. So if we have an independent voltage source, Vs, okay, so right now this is on. We want to have 0 volts for that source to be off. Okay, and so the question is not let's just make it 0 volts, but what does 0 volts look like in the circuit analysis world? And that looks like a short circuit, right? A short circuit has a 0 voltage drop. Okay, so we replace voltage sources with short circuits. Okay, so when we have a voltage source, we need to turn it off. We're just going to replace it with a short circuit. Okay, so a current source. Here's our current source, IS. In this state, it's on. When it's off, we want it to look like 0 amps, right? Okay, so what does 0 amps look like? it looks like an open circuit. Okay, so open circuit, no current flows, current is 0. All right, so to turn a current source off, we will replace the current source with open circuits. All right, this would be a very important thing to write down because I have seen students reverse this. Okay, so give yourself a little bit of a reminder, an important clue here, that we turn off voltage sources by replacing them with short circuits, and we turn off current sources by replacing them with open circuits. All right, so let's do kind of a simple example to start with. Okay. So this is 10 volts, 4 ohms, 10 ohms, 8 volts, 3 amps, and we are going to solve for this voltage Vx using superposition. Okay, there are 3 independent sources, so n is equal to 3. This means we will be solving for 3 parts of the voltage Vx, so there will be 3 parts to Vx, and we will be drawing 3 circuits, okay, one where each one of those sources is on and the other 2 are off. Okay, so this is the way I like to do these problems. Okay, so I like to start off by usually I tend to go from left to right, or I do all the voltage sources first and the current sources first. It really doesn't matter though. So I'm going to have the 10 volt source on. Okay, and if the 10 volt source is on, everything else in the circuit is off. All right, so with the 10 volt source on, we'll have that 10 volt source. We'll have this 4 ohm resistor. Okay, and I'm going to draw this at first, and then I'm going to erase some of this because we really don't need it all here, and I think it can get confusing. But I'm going to replace the current source with an open circuit. So I'm just going to open up the terminals where that 3 amp source was originally connected. Okay, and then I have the 10 ohm resistor, and then the 8 volt source. Remember, we just replace it with a short circuit. So I'm just going to draw a short circuit where the 8 volt source was. All right. Now, if it helps you to have these open terminals here where the current sources are when we turn them off, you can certainly leave them. I prefer not to keep them in the circuit. So I'm going to erase them. We don't need them for this particular technique, so I'm going to erase them, but I'll let you decide if you would like to keep them or not. So we have 10 volts here, we have 4 ohms here, we have 10 ohms here, and now we are solving for Vx1, the first part of the voltage Vx that's a function of only the 10 volt source. Okay, now I like to call these the subcircuits of superposition. So depending on how many independent sources you will have that number of circuits, subcircuits to solve for. We have 3 independent sources. We will have 3 subcircuits. And as far as how you get Vx at this point from the subcircuit, you can do whatever technique you like. In some cases, it might be simplification and expansion. In some cases, it might be voltage division. You might end up writing a mesh equation or nodal analysis. It's going to be entirely up to you. In some cases, you can look at it and tell by inspection. Okay? So for this circuit, and I'm going to do a variety of techniques, okay? If you really like nodal analysis and you really understand it, that's probably the technique you should use to solve these subcircuits, okay? If you hate nodal analysis and you find it very challenging, then don't use it here, okay? It's up to you. So I'm going to do voltage division here, okay? And oftentimes in these little subcircuits, voltage and current division is going to become a very common technique to find that voltage or current. So by voltage division, we have that Vx1 is equal to the total source voltage 10 multiplied by the ratio of the resistor we want to know about divided by the series combination 10 plus 4. All right, is the passive sign convention holding? Sure is. There's current's going to flow through this 10 volt source from minus to plus and then flow through the 4 ohm resistor from plus to minus. All right, so this is going to be 40 over 14 or 2.86 volts. Okay, so the first part of that voltage Vx. All right, so now let's have the 8 volt source on. Okay, remember, once the source has been on once, it is never on again. All right, so the 10 volt source won't ever be on again. So we're going to start by turning off the 10 volt source. We turn off voltage sources by replacing them with short circuits. Okay, then we'll have the 4 ohm resistor. We'll have an open circuit where that current source is. I'm not going to draw it. I'm going to put the node in though, just because sometimes it helps to see. Would have gone there, but we're not going to put it in. Here is the 10 ohm resistor, and then our 8 volt source is on. Yeah, and so we're going to solve now for this voltage, Vx2, which is the second part of that voltage Vx that's a function of only the 8 volt source. Okay, and I'm going to do voltage division again here because we still have a voltage divider. The source is on the other side of the circuit, but it's still voltage division. Okay, and so by voltage division, try that again. By voltage division, okay, we're going to have that Vx2 is equal to the total source voltage 8 multiplied by the ratio of the resistor we want to know about, 4, divided by the series combination of 4 and 10. Now, ask yourself this question: does the passive sign convention hold? This is the only source in the circuit here, so the current's got to flow in this direction from minus to plus in order for the source to be delivering power. And then it's going to flow in this direction, and so it's going to end up flowing from plus to minus. And so yes, the passive sign convention is holding. And so Vx2 is equal to 2.29 volts. Okay, so we've had the 2 voltage sources on, 2 different circuits. It's now time to let the current source be on. So now we're going to have 3 amps on. So we'll have a short circuit where the 10 volt source is. We'll have our 4 ohm resistor. We'll have our current source on. So this is 4 ohms. This is 10 ohms. This is 3 amps. This is Vx3, the third part of the voltage Vx. That's a function of just the 3 amp source. Okay, and I'm going to do some simplification here because between these 2 nodes, here and here, I have the 2 resistors in parallel. Okay, and so when I simplify that circuit down, I will have one resistor, and my current source. So here's 3 amps. This equivalent resistance is 4 in parallel with 10, okay, which is 2.86 ohms, 40 over 14. Okay, and here is our voltage drop, Vx3. Note that the negative terminal of Vx3 is at this node, the node that's at the head end of the arrow, and then the plus terminal is at the tail end of the current arrow. All right, so that's how we know we've got the current or the voltage labeled correctly. Okay, and so now when we look at this, we just have an Ohm's law equation to write. Vx3 is equal to I times R. So this is equal to 3 times 2.86 volt or amps times ohms, except that we need to adjust for the passive sign convention because the current is going to flow from minus to plus with respect to that voltage across the resistor. All right, so we've got to put a negative sign out in front to deal with the current, to deal with the passive sign convention for the resistor. And so when we multiply all this out, we'll get that this is equal to minus 8.57 volts. And so Vx is equal to Vx1 plus Vx2 plus Vx3. Okay, so we're going to sum all the parts to get the total voltage. So this is going to equal, when we drop in 2.86 and 2.29, so remember this is 2.86, this is 2.29, and this is minus 8.57. And when we add all of these together, we'll get that Vx is equal to minus 3.42 volts. Okay? So again, we use this to solve for a single voltage or current in a circuit. We would not use superposition if we were asked to, say, find all the voltages and currents in a circuit or to find power delivered or absorbed by every element. Okay, so this was a simple example. Let's work on one that's a little bit more challenging, okay? Yeah. All right. So, and this one is challenging more because it's not drawn in the way we would normally draw a circuit, okay? So this will take a second for me to draw here, and I'm going to give myself some starting points. All right, so here we have a 2 ohm resistor. Hold on, I'm going to make this just a little bit bigger. This is kind of small. All right, let's try this again. Okay, so this is a 2 ohm resistor. All the resistors are 2 ohms. Make it easy. And this is a 6 amp source. This is a 24 volt source. And this is a 12 amp source. Okay, so 3 independent sources. All right. So there'll be 3 subcircuits, 3 parts of the voltage we're going to solve for. And we're going to solve for this voltage. I'm going to put it in red to make it easier to see. We're going to solve for this voltage here, Vx, the voltage drop across the leftmost 2 ohm resistor. Okay. And we're going to use superposition to find Vx. We have n is equal to 3. So there'll be 3 parts to Vx, 3 subcircuits to solve. Okay, so I'm going to start off with the voltage source on. So we're going to start with 24 volts on. All right, so the 2 current sources are going to be off, which means that they will be open circuits. So I'm going to start with that center 2 ohm resistor and this 2 ohm resistor, and we will have this 2 ohm resistor. We will have this 24 volt source, and okay, darken in some of these nodes here. So only one source is on, the 24 volt source. So we have 2 ohms here, we have 2 ohms here, we have 2 ohms here, 2 ohms here, and 2 ohms here. And we are going to solve for this voltage, Vx1, the voltage drop across that 2 ohm resistor, the first part of the voltage drop across that resistor. That's a function of solely the 24 volt source. Okay. Now, oftentimes, especially when a circuit starts to look a little odd like this one does, it sometimes helps to redraw it and do some simplification. Okay, so I'm going to do that. So if we look at just the 24 volt source for a second, I'm going to draw that down here. And I am going to draw it in black. So here's 24 volts. All right, so let's come back up and look at this circuit. And let's put these nodes that have more than 2 connections here, all right, in red, okay? So, and that node is, I'm going to call this node 1 and this node 2. So here's node 1 and here's node 2 on the source down below, okay? So if we look on the left-hand side of the 24 volt source, so on this, not the left side, the up side, let's say, north side of that resistor, of that voltage source, we have these resistors, okay? And they're in series with each other, right? Because at this point, we only have 2 connections. So we're going to have 2 in series with 2. And so that's going to give us a 4 ohm resistor on the north side. And I'm going to box this up a little bit so it doesn't look so triangularly. So this is going to be 4 ohms that reflects that 2 plus 2 ohms on the north side of that, voltage source. Now, if we look on the lower half, the south half here, we have these 3 resistors, and they are all connected in series because we only have 2 connections at each node between nodes 1 and node 2. So I'm going to go ahead and draw that in here on the south end. So here we have 6 ohms. Okay, so when we do simplification and expansion, when we combine elements in series, we lose the individual voltage information. So what we're trying to solve for is no longer on this circuit, but it's not a big deal, okay, because we don't have to go any further than this. All right, so what we need is we need the current flowing in this direction, I, through that 2 ohm resistor to find Vx1, right? So we need this current flowing into Vx1. All right, that current I1 is the current that flows through these 3 2 ohm resistors. So if we were going to label that on the circuit that we've simplified, that's this circuit, or this current, right? I, flowing from node 2 towards node 1, all through those 6 ohm series combination of resistors. Okay, what's the voltage drop across the 6 ohm resistor? Well, if we look here between node 1 and node 2, we've got 3 elements here, and they're all connected in parallel, which means they all have to have the same voltage, okay, because they're in parallel, which means that we know there's 24 volts dropped across that 6 ohm resistor, just like there are 24 volts dropped across the 4 ohm resistor, because the voltage source here is in parallel with both of them. So we can write I then, I is equal to 24 divided by 6. Passive sign convention is holding, so I1 is equal to 4 amps. And if we take a step back onto this circuit, now that we know, and I'm not going to call it I1, I called it I. Let me take that 1 out. All right, and so now we know that I is 5 or 4, excuse me. We can go to this part of the circuit here and note that that Vx1 is equal to 2 times I, or Vx1 is equal to 8 volts. Okay, so that's the first part of the voltage Vx1 that's a function of just that 24 volt source. Okay, let's go to the next one. So for this next one, we're going to have remember the 24 volt source has been on, it can't be on again, so we're going to move to the 6 amp source. So we're going to let the 6 amp source be on. Okay, so again, this takes a second to draw out. Okay, so there's that 2 ohm resistor. Here's the short circuit where that 24 volt source used to be. We're open down to here, so the 12 ohm or 12 amp source doesn't exist because it's open. Here's a 2 ohm resistor here. Here's this 2 ohm resistor here. Here is the 6 ohm source. Here is this 2 ohm resistor. And here is this 2 ohm resistor. So here is 2 ohms, 2 ohms, 2 ohms, 2 ohms, 2 ohms, and I'm going to draw this 2 ohm above here. Here is 6 amps. Here is Vx2, the second part of the voltage Vx. It's a function of just the 6 amp source. Okay. Now, you can use any method that you like here. Any method at all is fine. I'm going to do some simplification. Okay, so I'm going to label some nodes here. There's one here that I'm going to call node A. There's one here that I'm going to call node B. And there's one here that I'm going to call node C. Okay, and these all have 3 or more connections. Now I want to point out that node B has a bunch of connections here. So it's connected in a bunch of places. Okay, I'm not worried about this node down here because those elements are in series. Okay, that's pretty obvious to spot. You might also have spotted that these 2 elements here are in parallel because they're both connected between A and B. All right, and so at A and B, we have 2 in parallel with 2, which is a 1 ohm product over sum. So 4 over 4. All right, we notice that these 2 here are in series. 2 plus 2 is equal to 4 ohms. So let's take that simplification and move down here, and do a little bit of simplifying. Okay, so I'm going to call this node A here, and this node B. And B, let's do it on the outside. And this node B. All right, so between A and B, we have this 1 ohm parallel combination connected. All right. I'm going to put C right over here. And then we have that 2 ohm resistor there for the 2 ohm, for the between B and C. Between C and A, we have our current source, 6 amps. And then between B and C, we also have that 4 ohm series combination. Okay, so we've taken this circuit here, done these 2 simplifications, and drawn this part, drawn the simplified circuit down below. Okay, we still have this voltage here across the 2 ohm resistor, Vx2. Okay, we can take this a step farther, because now between B and C, it's pretty easy to see that we have, not that, use the highlighter, that between B and C, we have 2 and 4 connected in parallel. Okay, so 2 in parallel with 4. That's equal to 8 over 6, or 1.33. Okay, ohms. So redrawing that as well. Here's C, here's B. And and here's A. So here's that 1 ohm resistor. So 1 ohm, 1.33 ohms. And then I can really draw this kind of straight. I don't have to draw it at that diagonal. I just have to draw the arrow correctly. So I'm just going to square this out so you can kind of see that I've grabbed this current source and I've just pulled it to make a right angle there. So here's 6 amps. Okay, now what about Vx2? Does Vx2 exist on the simplified circuit? It absolutely does, because when we combine elements in parallel, we don't lose the individual voltage information. So this voltage here is Vx2. All right, and so now what we have here is we just have a very simple series circuit where this 6 amps of current is going to flow through each one of these resistors. Now the 6 amps is flowing in this direction here. It will flow from minus to plus with respect to that voltage through that resistor. And so we will need to adjust for that with our Ohm's law equation. So Vx2 is equal to minus 6 to deal with the passive sign convention, multiplied by that 1.33 ohms. And so when all is said and done, we'll get that this is equal to minus 8 volts. So that's the second part of the voltage Vx that's a function of just the 6 amp source. All right, last, the 12 amp source needs to be on. Okay, what I would do at this point is I would pause this video, okay, and see if you can do this on your own. All right, so don't watch me, try it on your own, even if all you do is just draw the circuit. Okay, so pause that for a second and see if you can make that happen on your own. Okay, so with the 12 amp source on, I'm going to draw that part first. So I'm going to have a short circuit where the 12 volt source, 24 volt source is, excuse me. Here is my 2 ohm resistor. Here are a couple more 2 ohm resistors. here's that 2 ohm resistor, and here is this 2 ohm resistor. Yeah, so here's 2 ohms, here's 2 ohms, here's 2 ohms, here's 2 ohms, and here's 2 ohms, and this is 12 amps, and this is Vx3, the third part of the voltage Vx that's a function of only that 12 amp source. So you can solve this subcircuit any way that you like. Let's look at a couple of things here. So let's start off here with this part of the circuit here. So if we look at this, these 2 series resistors here, what can we tell about them relative to this short circuit where our 24 volt source was before we turned it off? Okay, this 4 ohm series combination is in parallel with a short circuit. Okay, current cannot flow back on itself. All right, so what that means is that this, we could also say this 4 ohm series combination is connected in kind of like a circle. All right, and current's not going to flow like that. It can't flow back through a node in a different direction that it started with. All right, so the 2 and the 2 are shorted out. And so I'm going to, we don't need them. They don't contribute to anything. Okay, so I'm going to go ahead and just take these out. Okay, actually, you know what I'm going to do? I'm going to redraw instead. I'm going to leave this here and make a note and say, so that these are shorted out. And so what we're going to have, and I'm going to draw it down below here, is we're just going to have this part of the circuit now. We've got this 2 ohm resistor. We've got this 12 amp source. We've got this 2 ohm resistor. We've got the short here where our source was, and we have this 2 ohm resistor. All right, so we have 12 amps here. We have 2 ohms here, we have 2 ohms here, we have 2 ohms here, and we have Vx3 there. Okay, and this circuit is, again, solvable using a variety of methods. All right, getting rid of these 4 ohms here up top makes the circuit a little bit easier to solve. I'm going to solve it using nodal analysis, because if I look, I've got a node down here, and I've got a node up here. I'm going to make the bottom node the reference node, and I'm going to call that V1. All right, and so my nodal equation is going to be, I don't care about Vx3 for writing the nodal equation. So the current flowing to the left is going to be V1 divided by the series combination of 2 and 2, so V1 minus 0 over 4, plus the current flowing down, it's minus 12. The source is sitting there, but it's in an opposite direction to what we want, plus the current flowing to the right, which is V1 minus 0 over 2. Okay, one equation, one unknown will solve. When we do that, we'll get V1 is equal to 16 volts. Okay, so we can solve for the current flowing in this direction, okay, because it's sitting right here in our nodal equation. All right, so this current, I'm just going to call it I. That current I is equal to V1 over 4, which is equal to 4 amps. So Vx3 is equal to 2 times I, although we have to put a minus sign out in front because the current I is going to flow from minus to plus with respect to that voltage. Okay, so we'll get that Vx3 is equal to minus 8 volts. So now Vx is equal to Vx1 plus Vx2 plus Vx3, and that is equal to 8 plus minus 8 plus minus 8. So Vx is equal to minus 8 volts. Okay. Now, what I encourage you to do is to go back and solve these circuits, maybe by trying different methods. Maybe they're ones that you're more comfortable with on solving these subcircuits. You can also solve every one of these circuits using nodal or mesh to check your work. Okay, so you're going to get the same answer for VX whether you use nodal, whether you use mesh, whether you use superposition. Okay, so this is the end of the concept lecture for superposition. I'll work a couple more examples on the example page for superposition in this module.